starting to go live. And I'm going to start the recording. Okay, hello everyone. Welcome to another another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the honor of having Dr. Sabrina Stierwalt from the Occidental College. Dr. Stierwalt, is an extragalactic, is an extragalactic astrophysicist. She uses nearby interacting galaxies to understand how stars and galaxies formed throughout the universe's history. Most recently, she was awarded a multi-year grant from the National Science Foundation to conduct the first systematic study of the gas dynamics and star formation in interacting dwarf galaxies, smaller galaxies which are the building blocks of more massive ones like our Milky Way. Dr. Stierwalt, thank you so much for being so kind and having accepted to give us this webinar today on such an exciting topic. So the floor is yours. You can start sharing and start when you like.
Thank you so much, Tasha, and thank you for having me here. I was super excited to join you. Let me share my slides. It's a little early morning here in Los Angeles. So my computer and I are both still waking up. Okay, so to me also, I am a professor, and so I'm super comfortable being interrupted. So please interrupt, or I'll try to keep an eye on the chat if you have questions. So thank you for having me. My name is Sabrina Stierwalt. I'm from Occidental College, which hopefully you see the slide, right? You see just the slide? Yes?
Yeah, we
okay, thank you. So I am Sabrina Stierwalt. I'm from Occidental College. In case you haven't heard of it, we are a small college in Los Angeles with only undergraduates. Some of our famous alumni include Fred Whipple, who is an astronomer who came up with the dirty comet theory, Barack Obama, who is the 44th president of the United States, and Ben Affleck, who recently married Jennifer Lopez. So I also importantly about Occidental College, as I mentioned, it's only undergraduates. So most of the work that I'm sharing with you is powered by undergraduate students. And so I've highlighted some of their names here because super proud of the work that they've done. So today I want to talk to you about the baryon cycle in dwarf-dwarf mergers and how we fuel hierarchical assembly. Maybe, there we go. So a key prediction of lambda cold dark matter paradigm for the universe is that we get larger structures from the merging together of smaller ones. So we see this in simulations of how do you form a massive galaxy like the Milky Way? You have to take smaller building blocks, smaller galaxies, and build them together to make a large galaxy. But lambda cold dark matter predicts that this should happen even at low galaxy masses. So we should see this merging together of smaller things all the way down the mass scale. We also see that most mergers in the universe occur between low mass galaxies. So big splashy mergers get a lot of attention, but most mergers in the universe are happening between low mass galaxies. We see theoretical evidence of this. I'm highlighting this plot on the left here that looks at the merger density. So the number of mergers per unit, a lot of things, per unit volume, per unit mass ratio, and against the merger mass ratio on the bottom. And so these are from the Millennium and the Millennium 2 simulations. And what they show is as you go up this to higher number densities of mergers, so more mergers, you get to these bluer and bluer lines where I've sort of marked it out with this little triangle. These are lower mass halos. We also see observational evidence that low mass galaxies are doing most of the merging at higher redshift if we're willing to link starburst activity with merger activity. And I'm going to talk a lot more about that. But if we're willing to say when we see starburst activity that's indicative there might have been a merger, then we see evidence that low mass galaxies are dominating these merger rates at high redshift because low mass galaxies dominate the starburst populations. And so here are two observational works, the UV luminosity function and looking at Hubble spectroscopy that show that in the lower mass regime, where I've marked it out in purple, that's where you see the most starburst activity and thus potentially the most mergers. We also know that mergers are a really important mode of galaxy evolution. So we see here, I'm showing some mergers from some massive galaxy mergers from work that I've done with the GOALS group. We see that these mergers result in increased starburst, higher AGN fractions, diluted metals, bluer colors. So in other words, when you have a merger, you don't just put one and one together and get a galaxy that is a larger version of what you put in. We really change the life of a galaxy when it's involved in a merger. But everything I've told you so far has been about massive galaxy mergers. Most of our studies have focused on what happens when massive galaxies merge together. But how do galaxy mergers proceed at low masses? This is something we're just starting to question and figure out. There are a lot of reasons why we might expect that they're not just scaled down versions of massive galaxy mergers. There are a lot of reasons we might expect that low mass galaxies, when they merge, the physics is fundamentally different. So we might get more interactions, but fewer mergers. So they don't have the same gravitational tug on each other because they're lower mass. So maybe you have a lot of flybys before eventual coalescence, and those flybys can do a lot of, have a different impact on those galaxies. Supernova feedback may be more important. We know that if you have a supernova go off in a low mass galaxy, it can really substantially affect the structure and the content of that galaxy, whereas in a more massive galaxy, it might not have as big an impact. The role of AGN may be less important. We know that AGN are ubiquitous, that we find them in all massive galaxies. But we have a little more trouble finding them in dwarf galaxies. This is a fast changing field, so we're getting better at looking for them, but they still are not quite as common as in massive galaxies. And so maybe the role of AGN in this merging activity is less important. We may have different dynamical timescales due to lower masses. We might have more dynamic processing. So massive galaxies have these stabilizing features like bars and arms that low mass galaxies just don't have. So it's likely easier to stir everything up in a low mass galaxy when it interacts. And we don't know if we get the same end product of a low mass merger. And I'm going to talk a bit about that today in terms of what we find. We expect massive galaxy mergers to end in these red quenched systems once they've burned through all their gas, but we are not sure that the same thing happens for low mass galaxy mergers. So we need to know more about dwarf-dwarf mergers as a population. How do these galaxy mergers proceed at these low masses? And one quick note I want to say on dwarf galaxies, because I know people come from all different scientific backgrounds that are listening. When I talk about dwarf galaxies, I'm usually talking about these pictures on the left here, star-bursting, gas-rich dwarf, we call them dwarf irregulars. But in case you're a reionization person or an early universe cosmologist, you might think of something like this on the right, these dwarf spheroidals that are older, gas poor, not forming stars. Usually this is not what we find in our sample, which you'll see why in a minute, but I just wanted to put that out there that I'm talking about this on the left, dwarf irregulars, and usually not these older, redder, deader dwarfs on the right. All right, so hopefully I've motivated for you why the dwarf-dwarf interactions themselves are interesting, but also knowing about dwarf-dwarf mergers is important for our understanding generally of galaxy evolution. So they dictate the degree to which the interstellar medium is processed before it's accreted by a massive host. If these little guys are merging together to form massive galaxies like the Milky Way, understanding what has happened in the evolution of these smaller systems is important to understand the Milky Way. The role of feedback at low metallicity, they can tell us about how effective are winds or turbulence or general AGN stellar feedback when you're in a galaxy that is low metallicity, very clumpy, just like these dwarf galaxies. They can tell us about the formation of intermediate mass black holes, potentially, and they can tell us how well the predictions of lambda cold dark matter paradigm apply at low masses. So these are all things that more broadly mean that it's very important that we understand dwarf-dwarf mergers. So some examples of dwarf-dwarf interactions or mergers exist. Here I've put a couple, and one of my favorites, NGC 4485, 4490, is this beautiful system here, sort of in the middle top. You can see these nice clumps of new star formation in the galaxies that are sort of facing each other, suggesting that maybe they were inspired, this new star formation was inspired by the interaction with the other galaxy. And of course, we have the large and small Magellanic Clouds, our nearest neighbors, that simulations suggest that they may have done some interacting with each other and fell in together into the Milky Way halo. But how representative are these examples? We know these very well. We've studied them in detail, but are they representative of dwarf-dwarf mergers as a population, or are they oddballs or outliers? So this is where my work has come in. I am leading a survey called the Tiny Titans survey. So this is a systematic study of interacting dwarf galaxies. So what do I mean by systematic? We look at the Sloan Digital Sky survey and we combed through the whole survey to find dwarf galaxy pairs. So here are our selection criteria. We require that they be low mass, so they have to be dwarf galaxies. And so our upper mass limit is something like the Large Magellanic Cloud. And then we require that they be close together. So their projected separation is less than 50 kiloparsecs on the sky. And their velocity separation, we also require that they have a spectrum. And so we know that third dimension, that they're within about 150 kilometers per second. And so Tiny Titans is everything you find when you search Sloan with those criteria. And I do want to point out this one important criteria at the bottom here, which is that we require that our dwarf pairs be more than 1.5 megaparsecs from a massive neighbor. So that's because we really want to understand what happens when dwarf galaxies merge with each other and not be tainted by an overall environment where there's a massive galaxy neighbor potentially influencing their evolution. And we do that because we know that massive galaxy neighbors can significantly affect dwarf galaxy evolution. So here are two plots that show us that. Christine Specken's work looking at the gas to stellar mass ratio of dwarf galaxies in the local group. So there's distance from the Milky Way on the bottom. And so you can see that within about 150, 200 kiloparsecs, you only have red points, meaning you only have dwarf galaxies that don't have any gas. They're these dwarf spheroidal systems. But it's only once you get out a certain distance away from the Milky Way that you start to see dwarfs that have gas, are forming stars more recently. So obviously being near the Milky Way affects the evolution of these dwarf galaxies. Other evidence of this from Marla Jiha's work shows that if you look at galaxies in the field, so these are galaxies not near other galaxies, all of the low mass galaxies have some sort of ongoing star formation. So this plot is showing stellar mass on the bottom and fraction of quenched galaxies that you find. So given a stellar mass, how many galaxies out there, what fraction of the galaxies out there in the field by themselves are quenched. In other words, not forming stars currently. And you can see that once you get down to the dwarf galaxy mass regime, roughly where these red points start to take over, you see 0 quenched galaxies. So this gets back to the question of what are the end products of a dwarf-dwarf merger? If dwarf mergers end in red quenched dwarfs, just like we think massive galaxy mergers can end in red quenched galaxies, why don't we find the red quenched dwarfs out in the field? So that's one thing we're trying to investigate. Okay, I do want to mention before I get into some of the Tiny Titans results that we have a couple of control samples. Every experiment has to have a good control sample. So we have our, as I mentioned, our dwarf pairs that we select very carefully from Sloan. And we require that they be isolated so we can disentangle the effects of being near a massive galaxy. But we also have a sample of dwarf pairs that are selected the exact same way, except they're not isolated. And so you'll see me compare these two samples throughout my talk in order to control for environment. So we want to see, would this have happened? Whatever physical effect we're observing for the Tiny Titans dwarf mergers, would this have happened if that merger was near a massive galaxy or not? And we have one other control sample, which is our matched unpaired dwarfs. So these are dwarfs that are identical to the dwarf galaxies in the Tiny Titans pairs. So they have similar stellar mass, they have similar metallicity, similar redshift, similar environment, except they're not in a pair. And so when you'll see that I compare to this sample as well, and the goal is to say, what if we are seeing some physical effect in our dwarf-dwarf merger, we want to ask, would this have happened to this dwarf galaxy, even if it weren't in a merger? And so we get that information by looking at these unpaired dwarfs in order to control for these stochastic processes, things that would have happened anyways. So if your eyes glazed over when I started talking about control samples, just know that we control very well for our results, and you can trust our results and what we find. So we're trying to do a lot with Tiny Titans. It's so rich for science. There's a lot of questions that we can address. And so I just want to highlight a couple here for you today. The first is we asked, does the frequency at which we find dwarf multiples match cosmological predictions? So because Tiny Titans is systematically selected, meaning it's not just a few scattered examples, we can make, not only can we say we see this happening in dwarf mergers, we can tell you how often it happens because we have this systematic sample. And so that's what we tried to do. First, so with Tiny Titans, we tried to look at the satellite mass function. So we've studied for a long time the satellite mass function of the Milky Way, right? How many dwarf galaxies are there of different masses hanging out around the Milky Way? We compare this to simulations. This helps us fine-tune our simulations and also improve our observations so that these numbers, we can bring these numbers to agreement. Now, I'm highlighting here some very recent work starting to try to determine the satellite mass function beyond the local group. So is the local group an outlier? Is it unusual? Now that we feel more confident in the satellite mass function here, what does it look like elsewhere? Is it similar to what we see in the local group? And we're starting to push this towards lower and lower mass hosts. Because under the lambda-cold dark matter paradigm, the sub-halo mass function is predicted to be scale-free. What that means is that we know very well that you have a massive galaxy like the Milky Way. It should have lots of dwarfs around it. But what if that central host is itself a dwarf galaxy? Well, lambda-cold dark matter tells us, well, that also should have a mass function. And so there also should be a halo mass function. So there also should be even smaller dwarfs hanging out around that central host. So work that I'm showing here has tried to characterize this mass function for the Large Magellanic Cloud. Obviously, we can see best our closest neighbors. So what galaxies, what do the galaxies that hang out around the Large and Small Magellanic Cloud, could they have been a dwarf galaxy group that fell into the Milky Way's halo together? And do our observations of the masses and the numbers of those galaxies match predictions from simulations? And here on the right, I'm showing the observations. Here are the more recently discovered dwarf galaxies hanging out around the Large and Small Magellanic Clouds in red. But the problem, of course, is studying the Large Magellanic Cloud and its satellites, is that it's right near this massive interloper, the Milky Way. So it's very hard to disentangle what are satellites of the LMC versus what are satellites of the Milky Way. When did different satellites join the group? So we asked, what if we could instead determine the satellite mass function in isolation? So what if we could take the Large and Small Magellanic Clouds and pull them out of the Milky Way's halo and see what kind of satellites they have and whether that matches predictions from lambda cold dark matter or not? So that's what we started doing with Tiny Titans. We identified 7 isolated galaxy groups with only low mass members. So these were some of the first groups found of galaxies that only have dwarf galaxies in them. And so here I'm showing pictures of a few of them. And so the way we found them was we looked at our pairs and we observed our pairs of dwarf galaxies with something called the Magellan tunable filter. So this is a Fabry-Perot that for observers, you can take your H alpha filter that's very, very narrow. It's only like 10 angstroms and tune it to where you think your H alpha emission should be in redshift space. And then anything that appears in your image, because the H alpha filter is so narrow, has to be within about 300 to 400 kilometers per second. So it's giving you, it's sort of like a rough spectrograph. And so once we did that, we followed up with a real spectrograph to get redshifts of anything that we saw in our image. And all of them turned out to be have redshifts that put them in potentially in this dwarf galaxy group. Okay, so now we know that we find dwarf galaxy groups. Discovering them alone was exciting. They're out there. Remember, these are isolated systems. So it means out there in the voids, there can be these little clumps of dwarf galaxies hanging out together and the dark matter that goes with it. So that was very exciting. But we want to take advantage of the fact that Tiny Titans is a systematic study. So we want to say, well, how often does this happen? How frequently do we find these groups? And do those numbers match with cosmological predictions? So that's what we looked at next. This is a very dense plot from Laura Salas. And so I will try to highlight so I've pulled numbers off this plot on the left to highlight the comparison to Tiny Titans. So the Salas work looked at given your host galaxy. So the colors are different masses of hosts. So we're looking at the blue and green lines for dwarf galaxy hosts. So primary galaxy in a group being a dwarf galaxy. How many satellites does that dwarf galaxy have according to simulations? And so Millennium 2, which the Salas work is based on, finds that the percentage of dwarf galaxies hosts with a mass around 10 to the 9, 1 to 3% of them should have a similar mass companion, which matches what we see with Tiny Titans. We see less than 5%. We have to do that little less than because we're sort of pushing the limits of Sloan sensitivity. So we hedge our our final number a little bit with a less than. And if we look at the percentage of dwarf galaxy hosts that should have satellites with mass ratios of 2% to 40%, we see that Millennium 2 predicts about 1 to 10%. So in other words, if you take a dwarf galaxy and make it the central galaxy of a group, 1 to 10% of those galaxies are going to have satellites that are roughly 2% to 40% of their mass. In Tiny Titans, we observe about 11%. So that's a pretty close match given our limitations of our surveys. So the conclusion from all of this is that when we look at the Tiny Titans dwarf groups and we compare them to cosmological predictions, they match. But we're only really skimming the surface here because Tiny Titans doesn't go nearly as deep as simulations can in terms of stellar mass, right? Tiny Titans is based on Sloan, and Sloan can only go so far, especially since we require that our dwarfs have spectroscopy in order to find them to begin with. We're only going down to sort of the most massive range of dwarf galaxies. So, okay, I will say this here. Let me go to this first. So we're only skimming the surface of stellar mass, and simulations actually predict that if we could go down a little bit lower in stellar mass, that we should actually find a lot more companions. So this is an example from the Fire simulation showing that if you have a central galaxy, that's a dwarf galaxy, we should see lots and lots of lower mass halos around that dwarf galaxy. So with Tiny Titans, even though we're matching cosmological predictions so far, which is great, we're only seeing the smallest number of dwarf galaxies. If we could get a little bit deeper in sensitivity, we should see a lot more if our observations match simulations. And so this is one project that we're working on with my students. So we got deep imaging using the Large Binocular Telescope, which I'm showing here. I just think it's really pretty, to get even deeper than the Sloan imaging can, and even deeper than our Magellan Fabry-Perot imaging went, to try to find lower mass galaxies that could also be satellites in these dwarf galaxy groups. Now, if there are any observers out there, you know that seeing a galaxy in our image doesn't mean it's in the group, right? It could be background, not likely foreground because all of our stuff is so close, but it could be a background galaxy. And so ideally you would get an optical spectra to place it within the redshift range of your group. But optical spectroscopy of very low mass things takes a very long time. So we couldn't possibly follow up on all of the candidates here you see in this image, for example, to see what their spectra are. So one of the things I'm working with a student on is, can we narrow down our candidate range, essentially get some idea of the redshift with just imaging alone? And this is something that will be useful for surveys like LSST, where you can't get all of you can't get spectra for everything. There's just not enough time in the world. And so the way we're doing that is we're looking at a plot of R-band magnitude versus surface brightness. So this has been done in Virgo. And so I had no idea if it would actually work in a dwarf galaxy group, which obviously has a lot less mass in it. But the idea is, if background objects should separate from foreground objects on this plot, because background objects are going to be fainter, potentially, and they're going to have higher surface brightness because you're taking the same amount of light, but if you move it back, right, it becomes more compact. So we expect background objects to be potentially fainter, but more importantly, redder. and also have higher surface brightness, be more compact. And we would expect foreground galaxies, so galaxies that are potentially in this group, to be fuzzier, lower surface brightness, and bluer. So here are some initial results from this work where my student made this plot where you plot R-band magnitude versus surface brightness. And so the known galaxy members, the group that we had already identified, are in blue, just using Sloan and our Magellan tunable filter. And so those are shown here in blue in both the image and on the plot. So you can see that they pop out somewhat above the other galaxies. So everything in this image identified as a galaxy is a gray point here. But I've highlighted in red galaxies that pop up above more than 2 sigma above the average value, the solid line. And you can see that they have lower surface brightness given their R-band magnitude. And so this is highlights that we can find candidates, galaxies that are potentially group members for, in other words, we're identifying good candidates for optical spectroscopy because we couldn't follow up on everything here. And so using a plot like this can help you identify better candidates for optical spectroscopy follow-up. And so that's our goal next, is to get optical spectroscopy of these galaxies and to see if they are actually in the group. And if they are, then we can compare them to simulations and what simulations predict at these lower masses. So that'll be very exciting. Okay, I'm just going to do a quick time check. Sorry. Okay, so I do want to touch on another, hopefully everyone's still with me, but if you're not, here's a great time to come back. Another thing that we're looking at with Tiny Titans, another question we're trying to address is, how do galaxy mergers proceed at low mass? Are they different than massive galaxy mergers? So the first question sort of looked at the numbers at which the frequency at which we find these things, but we're also trying to get into detail of the systems themselves and see if they look like massive galaxy mergers or not. So one thing that we know about massive galaxy mergers is that they can inspire powerful starbursts, like the antenna galaxies shown here. And then we expect their end products may be red quiescent galaxies. So the picture is that you have 2 gas-rich disk galaxies. They merge together. You get a funneling of all that material into the center of mass of the system. That inspires these powerful starbursts. It can inspire increased AGN activity, but eventually these systems burn through all that material in forming stars and fueling their AGN, and then you end up with a red quiescent system. So does this picture apply to dwarf galaxies at all? Well, the first thing we looked at is, do we get enhanced star formation in dwarf galaxy mergers? It's not obvious that we should, because they don't have as much mass as the massive galaxies. So maybe they're not as good at funneling all of that material in towards each other to get increased star formation. So our initial investigation with Tiny Titans found that yes, we do find increased star formation for our dwarf galaxy pairs. So that's what this plot is showing. If you look at the blue line, it's our Tiny Titans dwarf pairs. So pair separation is on the bottom. Given that we don't have any other information, no modeling information, we use pair separation as a proxy for merger stage. So farther apart earlier in the merger. As the merger progresses, they get closer together. So you move towards the left on this plot. And you can see that the star formation rate in these galaxies goes up as they get closer together. The blue line goes up. Now, the red line, we wanted to see, would this happen anyways for the pairs, for the dwarf galaxies that aren't in a pair. And so that's the red line. So for every dwarf galaxy in a pair that went into making this blue line, we found all its matches in the unpaired sample, and that's what makes the red line. And so if we plot the ratio of these two lines, it gives you the star formation rate enhancement. In other words, how much higher is my star formation rate because I'm a dwarf galaxy in a pair versus if I wasn't in a pair. And so that's what you see on the top here, the star formation rate enhancement. And interestingly, the star formation rate enhancement is similar, if not a bit higher than what we see for massive galaxy mergers. So not only is star formation enhanced in dwarf mergers, it may be even more so than in massive galaxy mergers. I also have a statistic here on the right. 20% of paired dwarfs are starbursting compared to 6% of unpaired dwarfs. So not only is the star formation rate enhanced, it is very much increased to be classified as an official starburst. So that raises the next question. So if there's all this extra star formation going on in dwarf galaxy mergers, are they shutting off their gas supply? Are they using up their gas? So we got H1 gas neutral hydrogen spectrum for every dwarf pair. And now we're going through and slowly trying to get gas maps. I've shown a couple here of these systems to try to look at what the gas is doing, because you might naively think if you have this higher star formation rate, it means you're going through your gas faster. And so here's what we looked at. On the left, if you just look at the plot on the left first, these are our isolated tiny titans pairs, and we looked at stellar mass on the bottom versus their gas fraction. So if these galaxies have higher levels of star formation and so are burning through their gas, you might expect these purple points to be lower down, meaning lower gas fractions, compared to the gray points, which are their matches that are not in pairs. But we don't see that at all. We see the purple points totally intermixed with the gray points, meaning that a dwarf galaxy, whether it's in a pair or not, its gas fraction is similar as long as it's isolated. But if you look on the right, this is our satellite dwarf control sample. So all the colored points are dwarf galaxies that are in pairs, but those pairs are near a massive galaxy. And so the gray points are their matches that are not in pairs, but are near a massive galaxy. So that's our comparison point. And you can see that, again, most of the colored points are intermixed with the gray points, meaning that whether you're in a pair or not, doesn't change your gas fraction, except we only start to see this lower gas fraction when we look at these dark blue points. So what are the dark blue points? Well, those are the pairs of dwarf galaxies that are very close to their massive host, so within about 200 kiloparsecs. So this tells us that being in a dwarf-dwarf merger doesn't turn off your star formation, and it doesn't affect your gas supply. It's being near a massive galaxy neighbor. So if you want to quench a dwarf galaxy, you have to put it near a massive galaxy neighbor. Putting it in a merger with another dwarf isn't enough. So this matches, so what is going on with the gas? If you have all this extra star formation, why isn't it gobbling up the gas? Well, we've done some dynamic modeling. Sarah Pearson leads this work of dwarf mergers that are very close, and so we can study them in detail. And what she finds is that the H1 gas is these dwarf mergers sit in very big extended gas halos. So the dwarf galaxies, the stellar components are shown in red circles, whereas the gas content is shown with the blue contours in this image. So what it looks like is that dwarf galaxy mergers are very, very good at spewing the gas outwards so that it sits in these big reservoirs and then slowly feeds back in over time. But it lasts for a very long time in these large reservoirs. So she uses the term that it parks itself out there and then slowly feeds the merger continuously over time. This matches what some simulations have found. So here's an example from the Eagle simulation that shows that satellite encounters are more, interactions between two satellite galaxies, two dwarf galaxies, for example, are more effective at removing gas and making these big gas envelopes than ram pressure stripping or tidal stripping by a massive halo. So these mergers between low mass things are very good at throwing out the gas. There's also some work by Alison Brooks and Charlotte Christensen that has shown that mass ends up more centrally concentrated post-merger for massive galaxies. So those are the systems on the right of this plot. But as you go to lower mass halos, the before is the open symbol, the after is the closed symbol. That might not be the case. So a merger between two dwarfs might not be as good at centrally concentrating all that material, and instead it spreads it out. We also see this in the star formation. So these are some beautiful Muse images of some of our interacting dwarfs. And we found that the star formation, here highlighted by some of these H alpha images, is much more widely distributed. We don't find generally a centrally concentrated star formation happening in these things. We see the star formation spread out throughout the dwarf and throughout the interaction. So what are the end products of dwarf-dwarf mergers? If you don't get the same thing as a massive galaxy merger, where you funnel everything into the center of mass and you burn through your fuel and you end with this red quiescent system, will the same thing happen for dwarfs? Well, I say here we might have to wait a bit longer to find out, because these dwarf galaxies have such high gas supplies. If you look at their total gas supply and calculate a depletion time from that, so how much gas does it have, what's its current star formation rate, given those two parameters, how long will it take to use up all that gas? The depletion timescales are quite high. So it might be that we do get red quiescent systems from these dwarf galaxies eventually. The universe just hasn't been around long enough to make that happen yet. Excuse me. To summarize some of the things that I've told you, hopefully I've made you at least piqued your interest in dwarf-dwarf mergers and convinced you that we have growing evidence that they progress in fundamentally different ways than massive galaxy mergers. So for example, we saw that star formation is more enhanced in these low mass mergers, and that starbursts don't always happen towards the end of the merger. We see them at a large range in pair separation. We see that the mergers between the dwarfs don't effectively shut off their gas supply, as we think happens in more massive systems. They still have these big gas reservoirs. And we see that star formation is more likely to be widely distributed throughout the galaxy rather than centrally concentrated, like we tend to see in massive galaxy mergers. So I think I have maybe a couple more minutes. I just want to highlight a few projects that I'm super excited about that we're doing now. Another question we're asking is, so we have enhanced star formation. What fraction of that happens in clumps versus more spread out? Because we think in the early universe, high redshift galaxies were super clumpy. We also think they were low metallicity and merging, which is what Tiny Titans is. We have a low metallicity merging environment. So we're trying to understand how feedback occurs in this clumpy star formation regime, so that we can maybe make comments on what's going on at high redshift. We also have a really exciting Hubble program where we're trying to address why some dwarf galaxies have really large star clusters. So here's a plot that inspired this project, which is star formation rate of a galaxy on the bottom, and the magnitude, how bright is the biggest cluster in that galaxy. So bigger galaxies go to the right, higher star formation rate, bigger galaxy. You expect bigger galaxies to be able to have bigger clusters, right? So you expect some sort of linear relationship here, which you do see for the most part with these black points. But you see a couple of these red points here which are in dwarf galaxies. And so there are some dwarf galaxies out there that have very large, we call them superstar clusters, that they have no business having, essentially, because they're so little. How did they make such a big cluster? And so one of my theories is that, I'm going to skip over that part, is that dwarf-dwarf mergers potentially affect the cluster mass function and can produce these big, massive clusters. And so here's one of our HST images from a merging pair, and showing the different colors from our imaging. And you can see that they're really nice H alpha in green, these clumps that sort of face each other in the galaxies, suggesting that maybe they were inspired by the interaction. And so we're starting to look at the cluster mass function for these things to see if the most massive cluster in these dwarf galaxies changes if you're in a merger or not. And so I'll highlight, so going back to this plot, now I've thrown on those dwarfs that I just showed you, where their most massive clusters are. And you can see that they sit above this relationship as well. And we've started doing this work for a few more tiny Titans dwarfs, and this is where they lie, the blue stars. So some of our interacting dwarf galaxies do in fact host these unusually large superstar clusters. So we've just started this work, and so we want to continue to compare dwarf-dwarf mergers versus non-interacting dwarfs, and do a more detailed comparison of their cluster mass functions and see what merger activity does to a cluster mass function. And I'll say we do, and we're also looking for AGN because we know massive galaxy mergers can inspire AGN activity. So since we want to find lower mass AGN, why not look in dwarf galaxy mergers to see if they also inspire AGN activity? And so we've done X-ray. So we looked at dwarf galaxies that have unusually red wise colors. So lots of big caveat, lots of things can give you a red wise color. But we followed up the reddest ones with X-ray observations. And here's an example where we found a nice hard X-ray source in one of these dwarf galaxies. So we're doing a multi-wavelength campaign to try in the radio continuum and all sorts of different wavelengths. So stay tuned for that. So I'm going to put up this slide again that tells you about what we're trying to learn more broadly with Tiny Titans, and then highlight some pictures of my students who have done most of this amazing work. And I will stop there and say thank you very much.
Thank you so much, Sabrina. That was lovely. I'm still trying to get my head around everything that you said.
It was a lot. It was dense.
No, but this is very interesting work. All right, let me get back to Zoom. Okay, sorry, I'm just trying to look at the chat to see if we have any questions posted. No, I don't know where the chat has ended up. Okay, so I'm just going to ask participants, if you have any questions, you can raise your hand. And then I'll call out your name and you can unmute and ask them. If you're uncomfortable asking questions by audio, you can put them in the chat as well. And I'll get to them as soon as I find the chat. Okay, so maybe we can go first with Marco.
Hi, Marco.
Sabrina, thank you very much for the very interesting talk. I have two questions. I think I missed one point. When you showed the groups detected with H alpha, how big are these groups? I mean, how many galaxies dwarf galaxies do they host?
That's a great question. Let me see if I can. I don't know if I can go back that way. So they are fairly. Sorry if I'm making anyone dizzy. They are. Where's my image? So the groups originally identified right? So they were a pair. And then we looked around our pairs to see how many had potentially other members just from looking at Sloan. And we found 7 and that were worth following up. And so when we did our Fabry-Perot, our very narrow H alpha, we found that they had sometimes there were just 3. So I don't know if you can see my mouse. This one just has 3. This one has 5. So they have between 3 to 6 dwarfs. So we call that a group. But so then what we're trying to do with our additional imaging is there more? Are there more galaxies here? And obviously you don't know that they're actually associated just from an image, and even with redshift information. So that's something that I sort of skipped over. We looked at the Illustris simulation and we see that there should be contamination from projection effects. So you can still get things, even when you have redshift information, that look like they're hanging out together, but they're just ships passing in the night, right? They're not actually gravitationally connected. And so one thing we're trying to do is we've started mapping them with H1 to see if they have the kinematics connect them to each other or not. But they are at least within, I'm trying to remember because you asked the sizes.
No, I didn't ask for the
okay.
How many members? I mean, it was my
yes.
my
okay.
request.
Okay.
6 dwarf galaxies. It's a lot. I mean,
yes.
So it's a big group.
Yeah.
And have another question.
Yes.
From the Muse data, do you have information on the metallicity maps? Do you find weird gradients, weird metallicity gradients, or metallicity deeps? I don't know. Can you comment a bit more about those data?
That is something that I very much want to know, and we don't have those yet. So George Pervon is leading the Muse work, and so he's making progress, and he's just started working on that now. And so we should have information on metallicity soon. But we don't know yet. But yes, looking if there's a gradient, if how the gradients match. So this system is one of our later stage mergers. So here he does a model of it in this paper, but here's one system and here's the other, right? So it'd be very interesting to see what those metallicity gradients look like.
Thank you very much. Very, very
I'll send it to you when we get it.
We have a question from Rodrigo as well.
Yes, thank you, Tassia. Thank you, Sabrina, for such an amazing talk.
Thank you.
I have some very basic questions from someone who is from the other extreme, the solar system.
I love basic questions. They're often the hardest.
Well, there was this slide where you show the members, the radial velocities where you identified the members. So what is the limit? I saw that what is the order of magnitude to say that a particular galaxy is a member of the group?
That's a good question. There's no nice limit. So we have to rely on some estimates, physical estimates. So one thing you can say is, are they gravitationally bound to each other, right? So we can look at how fast their relative motion is. This is solar system, right? It governs everything. How fast you are going tells you how much mass there has to be there to hold you in place. And so we can sort of estimate and say, well, we can estimate the relative velocities given how much mass is there. Is that enough to hold them potentially in place, right? Could they be gravitationally bound? So we've done that estimate, and the answer is yes, they could be gravitationally bound. But of course, we don't really know their relative velocities. We're sort of guessing because we don't have the velocity in this direction, right? Like in 2D space, we only have the 3D velocity difference. And so we can do, and so this was a Nature astronomy paper. And so I go through that exercise of, let's make a 3D projected velocity and try to guess at their relative velocities with each other and see if they could be gravitationally bound, because they're not very massive, so there's not a lot of mass there to hold on. We can assume that there's some dark matter there also to help, and maybe some H1. And so when we put that all together, they are consistent with being gravitationally bound, but that doesn't mean that they are. So that's why we're trying to get the H1 maps. Still not totally, you're still not totally sure after that, but you can at least, if you see H1, like the kinematics being consistent, right, in this H1, because the H1 spreads out, it extends much farther than the stars. And so if you can see it connecting and the kinematics matching up, then that can tell you that maybe they are actually connected as group members. So that's something we're trying to do. But for the Fabry-Perot filter, it says they're within 400 kilometers per second of each other, and that's kind of a lot. So that I wouldn't believe anything beyond that. And even within that, it's still not sure. That's why we went back and got more fine-tuned optical spectra.
Sure. Well, thanks.
Thank you.
I have two more questions, if I may.
Yeah.
Okay. You were showing identifying the lambda CDM. You were showing what will be the masses of the satellite galaxies, and showing that it was around 11%, but the predictions were around 5%. My question is, couldn't it be more or less because of the limits, observational limits? Maybe you aren't seeing something that it's smaller.
Yes.
Or do we guess something of any value that could be?
Yes, definitely. So simulations can tell us a lot more than observations at the low mass scale, right? Because they can go a lot lower than we can, especially when we're trying to get outside of the local group. So a lot of people, when they study dwarf galaxies, they're a lot closer than these systems, because we make sure that our tiny titans are isolated. They're a lot farther away than other typical dwarf galaxy studies. And so that means we can't see as faint things. And that's why we need all this extra imaging. And so with Sloan, even with the Sloan survey, we're pushing the lower mass limit of the survey. And so that's, for example, why we have the less than 5%. We have some observational limits with the spectroscopic survey and everything. And so we suspect we can classify this in my second row of this table. We can classify that pretty well, because it's saying if you have a massive host that has 10 to the 9 in stellar mass, so that's like roughly around the Large Magellanic Cloud, a little bit less. How many satellites does it have that are within 2% and 40% of its mass? 2%, you're starting to hit the lower limit of where Sloan can tell you what's there. 40%, it can still classify that pretty well. So I'm willing to put my name on this 11% in this mass range, but anything lower than that, we really need deeper imaging than what Sloan has to offer. So, and the predictions say there should be more there. And that's why, so this Laura's Sales's work, you see the plots going up as you go to lower mass ratios. And so that means we should see more things there, the lower you can go down in mass. And so that's what I'm trying to be able to answer your question even better, right? This is how many we miss, and this is the increase that we see.
Sure. Well, thanks.
Yeah.
And my last question is about the.
Sorry.
Okay.
Before you go on, I just want to ask the audience, maybe one of our junior members of the audience have any other questions that they want to ask? Okay, I don't see any more raised hands. Okay, so you can
always
go
email
ahead.
me.
No, it's a very simple question. That you showed that in isolated dwarf pairs as well with dwarf galaxies that are close to big galaxies, the star formation rate is powered up. Does gravity drives this? What is the explanation of the star formation rate being?
That's a great question. Yes, we think that is what happens. So the picture, so we need the short answer is we need more models of dwarf mergers. People are just starting to model dwarf mergers. I'm not a model or a simulator, so but people are just starting to do it. But because I had that slide of like all the reasons we think low mass mergers might be different, all that comes back to the fact that their gravitational potential wells are shallower, right? They have less mass, so they have less gravity. And so we think that I guess the physics is still the same, but how that turns out for a dwarf galaxy could be very different than for a massive galaxy. And so the picture we have in massive galaxies, at least, is that when they merge, all of their stuff, their dust, their gas, their stars, sort of gets funneled together into a shared center of mass, right? And so when that happens, right, how do we get stars to form? You compress gas clouds.
Yeah.
So if you're slamming a bunch of material into each other, right, you expect that you would get more collapsing gas clouds. You can inspire these powerful starbursts. And you do see off-nuclear starbursts in some massive galaxy mergers, but most of them settle out eventually into this centrally concentrated starburst. Whereas in the dwarf galaxies, we see the starbursts popping off all throughout. And so the question is it just because they have lower mass, they aren't able to centrally concentrate it, or maybe they just need more time? And eventually that would happen as well. But because of this H1 reservoirs parked, and because they don't have nice bars or arms that like to bring things together, maybe it's a combination of all of those things. But all of it comes back to gravity, as you said.
Okay. Well, thanks. Thank you very much.
Thank you so much. Thank you for all the great questions.
Sabrina, thank you for staying 6 minutes longer. I have to say, your excitement is contagious. I love seeing people very, very excited about what they do.
Thank you.
Okay, so due to the time, I think we can wrap this up. This presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very, very special thanks to you, Dr. Stierwalt.
That's right.
Okay, yeah. Sorry. So thank you once again, everyone. Have a great day, stay safe, and I hope to see you all again in our next webinar. Thank you very much.
Thank you.
Thank you. Thank you very much.